in the in trying to provide you with every possible way these problems can be permutated, here's the first one. And this is not terrible, but it does add another layer of complexity, right? Something else that you have to remember to do and something else that you have to account for. So there's a variety of ways questions can be phrased here. But more importantly, this is the way the universe actually works. So I'm happier doing problems like this because it's more realistic. The truth is, if there's enough static friction, the system doesn't move anywhere. But if there's not, then static friction gets broken and the box begins to slide. So what I want to ask first is, if I just set this system up and let it go, would it start moving or not? That's the first question. We got to figure out if it would or not. That's a static frictional problem because we're trying to see if there's enough unbalanced force to break the static friction. So let's start with a static friction question. And I'm going to do something to help your notes because I think you're just so used to having somebody help you with your notes a little bit. So in this first part, we're going to be talking about static friction and the questions surrounding static friction. And the way in which we use this in the real world is we want to know, remember, static friction is an inequality. So the static frictional force will increase to try and hold the box in place, but there's a limit as to how much static friction there can be. But when we're talking about static friction, we're talking about a situation in which the box is not moving with respect to the surface. So since the surface is the table, we're talking about a situation in which the net force in our system will be zero. But we want to see if there's enough frictional force there. Now, there's easy ways to kind of go through this problem without using our set of steps. But the problem is when we leave our set of steps, you have to start rationalizing the problem. And some of you, I think, have a hard time with this. But hear me out. Do we know the only box that's experiencing friction is the blue box, correct? And the blue box is also the only box that has a normal force acting on it, right? We know right now the size of the normal force on the blue box, don't we? So we could, again, I am not doing my set of steps right now. I am just reasoning this problem out. The normal force on the blue box has got to be equal to the weight of the blue box because in the y direction, the net force is zero. Does that make sense? That also means that the normal force equals 300 newtons. Yep.
Why would it be energy equal to kilograms?
Well, because we're looking at a weight. So,
Oh,
right, this is going to be weight, and this will be normal force, and this will be tension. So, in looking at the y direction, I still have to take the 30 kilograms and convert it to a weight. So we talk about the force. Oh, no worries. So what I'm saying to you is consider this. The static frictional force has to be less than or equal to 0.5 times 300. Again, I'm not using my set of steps. I'm just rationalizing the problem. This means the frictional force that I have to work with is up to 150 newtons. I'm just doing the math. Now the question is that frictional force enough? Like, will that be enough to hold the box in place? Now, to answer that question, I got to figure out, well, how much is pulling on the box? Because I know how much friction I have to work with, but what's the demand? Well, I'm thinking that the tension acting on the blue box is the same as the tension acting on the red box. But since the net force is zero, isn't the tension going to be 150 newtons as well? Right? if the system's held in place, then wouldn't the forces on the red box be balanced? And if they're balanced and the box weighs 150 newtons, I think there's 150 newtons of tension in the cable. Well, that puts us in a weird position, doesn't it? Because it looks like we have friction can only be up to 150 newtons. We're pulling at 150 newtons, but that's a less than or equal to sign, which means I think the box stays in place. Don't you guys? Now again, I didn't use any set of steps. I just came at this problem and tried to rationalize my way through it. Your set of steps would also have found this answer too. But if you have never used your set of steps correctly, but understood what all this is about, you could rationalize your way through it. Now, I don't know if that worked for you or not. If you want to use your set of steps, we could use our set of steps. It's going to get the same conclusion, though. So right now, the answer is if I let it go, it'll be right there on the edge, right? Just about to go, because we're right at the threshold. We're applying just enough force, but friction is just big enough to hold it in place, right? That's when you lifted the shoe up on the book, and it just started to move, but wasn't moving yet. That's where we are. We're right there on the edge. Any tap to the table, any tap to the mass, and it starts moving. And the moment it starts moving, kinetic friction takes over. Is kinetic friction more or less than the maximum amount of static friction? See, I have two schools of thought on it, apparently. But if I look at the coefficients, is the coefficient of kinetic friction greater than or less than the coefficient for static friction? Less, which means the kinetic frictional force will be less. But it's not an inequality. Once we start sliding, friction is a constant. It stays the same the whole time while you're sliding. So if I just tap the box, the frictional force becomes less. So now my question would be, what's the acceleration of the boxes once we break static friction? And does it speed up or slow down? I don't think you can answer that one through rationalization. I think you have to solve that one. And I think your set of steps is for that one. So let's do that problem. We'll do that one together. But I think we should start by recognizing the moment we break static friction and the system starts sliding, we're going to need to look at a second law problem. So we break static friction, the thing starts sliding, so kinetic friction takes over. What's the acceleration of the system, and is it speeding up or slowing down? Well, I think a free body diagram's in order, don't you? One for each box. So I already have one. It's kind of messy, but I'll keep the one that's there for the red box. The blue box, I erased it, but I'm going to redraw it again with a downward arrow for weight, an upward arrow for normal force, sideways arrow for tension, and a sideways arrow for friction. All look good to you guys? Write yourself a set of relationships. I want to come by and see them. It's a process. You do need to follow the process. Are you okay with these free body diagrams? So I have two different boxes, but I'm going to have lots of things I have to deal with these boxes. So let's start with the blue box, since that's got the most stuff happening, right? In the x direction, I believe that's going to be the direction of the acceleration. So I'm going to put net force in the x direction equals ma. Does that make sense to you guys as to why I'm doing that? But net force in the y direction, I'm going to put equal to 0 because I don't think it's accelerating up or down. In fact, we're forcing it to be that way. Now, that means that the normal force equals the weight. And I'm doing all that in blue because that's the blue box. That way, we can kind of separate out my notes a little bit. I know the weight of that box because it's 30 kilograms, so it's a 300 Newton box. That makes the normal force 300 Newtons. We already knew that. It was all up here, but just going right from the first step and walking all the way through. In the x direction, there are two forces. There's tension and there's friction, and that equals ma, but m is 30, so 30 times a. Now, normally I'd say we'd be done there. We should move on to the red box, but I've got friction in play, so I'm going to have to do something with the friction. But we know something about friction. It's not a mystery. Friction equals mu times a normal force. And we know what mu is, and we know what the normal force is. So this isn't a mystery. We know how big this force is. I mean, yeah, we could do the substitution first and plug the numbers in later, but maybe for some of you, this is the time to figure out how big that force is. Mu is 0.3, and the normal force is 300. So 0.3 times 300. I think it's 90, right? So this will be 90 newtons. So down here where I have tension, that means tension minus 90 equals 30A. All right. Now I think I'm done with the blue box because there's nothing else I can do here until I figure out how fast the system is accelerating, but that involves the red box. So let's talk about the red box. I think there's only two forces acting on the red box, but I'm going to make this the positive direction because I made this the positive direction for the blue box. So for the red box, I have 150 newtons downwards. That's the weight of the blue box. The weight of the red box. And I have tension upwards, and that has to equal MA. Well, M is 15. Well, that's it. That's all there is we can do with the red box. But that's okay, because we're trying to get something that had the tension and the acceleration in it. And we have that now. So I think bring these two things together and use them. It's a system of equations. I have two unknowns and two equations, so I've got enough. I'm going to add them together, and I'll get 150 minus 90 equals 15 plus 30 times A. Remember what I told you. Every one of these problems will eventually have the sum of the mass in it. So look for that. And there will be a point where you will see the external forces. Well, the external force is the box hanging off and the friction on the table. Those are the external forces. This is it. This is all there is. So I subtract. I think you guys can do that, right? 60. And that equals 45A. Now, if I had subtracted and this was negative, then my box would be slowing down because friction would have been greater than the weight. And if I subtract and I get a positive number, that means that the system's going to be speeding up. So don't be worried if your answer is negative. So if the friction was bigger, it just would have slowed the box down until it stopped. But in this case, the friction isn't big enough to do so, so the box accelerates across the table. How much? Well, 60 divided by 45, right? Let's see, 4/3? Is that right? Bless you. So 1.3 meters per second squared. I think it's 12/9, yeah, 4/3. All right. What are we thinking? I mean, does adding friction make it harder? Yeah. Yeah, most certainly it does. It adds a layer of complexity. Is it outside our boundaries? No, it's inside our boundaries. This is a reasonable one. So how many layers of complexity do you think we can put together? And I don't mean this in I'm trying to be mean kind of way. I mean, what do you think the AP Physics 1 curriculum requires of you? It requires this of you. This is well within our boundaries. Does it require one where the table's on a ramp? Now, that might be a bridge too far, but it's inside the curriculum. But that would be the top end of the curriculum. Is it okay for the table to be a ramp without friction? Yeah, that's well inside the boundaries of our curriculum. But again, there are edges. Do you understand what I mean by that? So they could, and I say they, but I mean I could on a test give you the inclined plane problem from yesterday and add friction on it. That is within the boundaries, but that would be the maximum level of difficulty. I think this is well within the boundaries of what I expect of you. This kind of problem. Whether it's this one or even